Recording, resume. Okay, so back a few days ago, we were doing this one where the ball bounces off the floor. I think here's what I do. I'm just going to show you guys these notes, and then I'll pull up a blank piece of paper and we'll solve a new one from scratch. And then my other AP class do the same thing as we'll go through another one of these. Okay. So they told you the drop height and the rebound height. Okay? And they also told you the time of this collision, which is a tiny, tiny fraction of a second. Right? They told you some number of milliseconds. Oh, okay. Some number of milliseconds. So you have to convert that to seconds. Right? Divided by 1,000. Okay? Uh, and if you want to know like something about force, like what's the force due to that collision, that bounce, right? Um, well, this is where you have to bridge kinematic motion and dynamic motion. Right? So we got to figure out what's the crash speed versus the rebound speed so we can get the change in velocity. Right? Keep in mind the direction changes. You just have to like subtract a negative kind of deal, right? Right. Change in velocity. Right? And then if you take that change in velocity, divide by the time of that collision, they'll give you the acceleration. Take the acceleration multiplied by the mass, F equals ma, you'll get something to do with force, right? Right. So let's see, if you know the drop height and the rebound height, you can use this third kinematic expression right here to calculate what is the crash speed and the rebound speed, right? Right. When Galileo was dropping stuff off the Leaning Tower, how fast were all those objects hitting the ground? Square root 2gh, where h was the height of the tower. Okay? This expression right here, the crash speed is square root 2gh, as long as you start from rest. Balls at rest here and also at rest here, right? Uh, hold on to this expression in your back pocket because this shows up all over the place in physics. Right? Something to do with square root 2gh is could be like the crash speed if you drop it from some height. Okay, right? This shows up all over the place. It's going to show up again in this class sometime, probably multiple times. Okay, so right. Right. The fact that it reverses direction because rebounds, baboing. Right? If you want the difference in velocity, right, you got to do square root 2gh minus the negative square root 2gh. Right? So here, I plugged in the values for all these particular heights. I got like, it was crashing at like 12 point something meters per second, and it rebounded at 10 meters per second. Right? But guys, what's the difference between 12 down and 10 up? And it's not 2, it's what? 22, because you have to like subtract a negative. You have to do 12 minus negative 10 because it changes direction. Right? Yeah. Right, so 22 and change meters per second. Right? So there's your change of velocity. Now, acceleration is that per time interval that happens in. So you can get this crazy bonkers acceleration. Okay. Right. So we got this acceleration, right? F equals ma. Right. Right. Once we know that, all you have to do is multiply by the mass to get the force. Right? I should say this is a net force, and it's also an average force. So it's like an average net force. Okay, you guys got that? Right. That m times that a will give you the average net force. Right. And so a little bit more on that, something to do with average net force. Okay. So do this graph here. So force versus time. If you're looking at that collision, let's say I had a super slow-mo camera, and you're watching that collision happen. Ball starts to make contact, starts pushing, gets like maximal squash, and then starts rebounding, and then finally leaves the ground. Right. If you made a force versus time graph, this graphs tend to look kind of like this. Right. Kind of like this. Right. So bam, 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 something like that. Right. And all this math we did with Newton's second law of motion really tells us something about the average force, which is probably approximately half of the maximum force, right? So if you were told like this ball has maximum strength of like, let's say like 4,000 newtons, right? As long as you don't put a force greater than 4,000 newtons, it's not going to like break apart. It's not going to bust apart, right? Well, did the ball bust apart? Well, here I'm looking at like about 3,400 newtons. You're going to say, oh, so it's all okay. But keep in mind, the maximum force is probably about twice that, right? The other little detail to keep in mind, and your quiz question version of this is a little bit simpler than this, right? Is that this is a net force, right? There's actually two forces acting on the ball at the point that it's colliding with the ground. Right? There's the normal force from the ground that's causing it to reverse direction, but don't forget that the weight is also acting there. Right? So the actual normal force from the ground is actually a little bit bigger than this because you have to, here, I'd have to say something like the net force is the normal force minus the weight. Therefore, what's the normal force from the ground? Well, you could rearrange this and get it'd be the net force plus the weight of the ball. Okay? Now, the weight of the ball was about 4 or 5 newtons. So if you add 4 or 5 newtons to that, you get like what 3402 newtons, something like that. Okay? So the actual force from the ground is a little bit bigger. Okay? Okay. Let's do exactly that question. Oh no, you know what? I know what I'm gonna do. I'm gonna give you guys a slightly more complicated version of this. That's what I'm gonna do. All right, we're gonna bounce a ball off a wall. We're gonna bounce it at an angle. Right, kind of stretch your guys' imagination a little bit. Okay. You guys remember too that all these solutions are on Google Classroom, of course. Okay. So, so I got my own example here. Let's suppose here, let's get a Cartesian system right going on. Right. Suppose you're bouncing a ball off a wall. Right. Bounce here. We should spell that out. Bounce a ball off a wall. Right. And let's keep it kind of simple. Let's say this collision happens to be what's called perfectly elastic, so it doesn't actually lose any speed. Okay. So I'll have here. Let's have V collision be like how about 20 meters per second, right? And a V rebound. Right? Now these are speeds, right? So also 20 meters per second, because I'm just telling you the magnitude there. Okay. Now it could be a vector, like a velocity vector. I also include the direction. So let's suppose this angle right here is like 60 degrees, right? Or if you like, what would that make this angle right here? Yeah, 30 degrees, right? Right. From that long. Okay. Like I said. Right. Ooh, I bet it's a similar story over here, right? What do you guys think that angle is? 60 degrees. This would also be 30 degrees, something like that. Great. Okay. So I guess that. Let's say that the mass of the ball is like 0.45 kilograms. That's a baseball right there. Right. And the question is, what is the force of the wall on the ball? Right, so there's your question. Okay. Okay. What force? What force interaction during the boing right there? What force interaction? Okay. Okay. So this is really similar to those notes I was showing you, but it's got that extra complication of 2 dimensions, right? Negative 2 dimensions. You know what? If you can stay a step ahead of me, then it's probably a pretty good idea. Stay a step ahead of me. Right? First thing I'm thinking is I'm going to break these velocity vectors into components, because the ball was initially headed sort of towards the wall and sort of along the wall. Right? So I'll break that into components. And then after it rebounds, boing, it's still traveling along the wall, but now it's traveling away from the wall, like that. That'd be true too. All right, boing, just like that. Right. So I could call this V initial in the x direction and call this V final in the x direction. Okay? Guys, that the force from the wall, which direction does the force point? Yeah, to the right, right? Because it's a what kind of force starts within? Normal. It is a normal force, isn't it? Right? And you guys know normal force always points perpendicular. It's in the name, right? Normal is perpendicular. That force from the wall is pointing straight perpendicular. Which is why, say, it doesn't change what the ball is doing in the y direction here, right? Maybe this is like aerial point of view. I don't care anything about the weight of the ball, right? We're just like looking down on the situation. But possibly friction could act. Maybe it starts to spin the ball, but let's not even worry about that, right? Right. So all I care about is the normal force from the wall. Right? Maybe I should say what's the normal force from the wall, right? Right? Who can tell me what is this right here equal to? 10 meters per second. How'd you know 10? Yeah, sine of 30 is 1/2. And this right here is a sine relationship. Yeah. So this is 20 meters per second times sine of 30 degrees, and sine of 30 degrees is 1/2. So that's 10 meters per second to the left, right? Okay. Well, by symmetry, what do you think this is right here? 10 meters per second to the right, right? Wouldn't that be true? Like that, right? Pretty good. Right. So let's see, if I want force, I need to know mass and acceleration. Oh, well, here's the mass that was given. So if only I knew the acceleration. Oh, I did forget to tell you guys one thing. There's one more thing you need to know before you can actually solve this. What is it? The time interval, the time of that collision. Right. Let's go. How about 2 milliseconds. So that's 2,000ths of a second. So here, maybe we'll call it delta t, like the time of collision. Okay. Okay. So let's get acceleration so that we can get the force. So the acceleration is going to be change in velocity per time interval. Okay. That's going to be, ooh, guys, what is the change in velocity? Yeah, 10 minus negative 10 would give you 20, wouldn't it? Right? So going 10 meters per second minus negative 10 meters per second, which is 20 meters per second. And it all happens in, say, 2,000ths of a second. Like that. Okay. So let's see, what's 20 divided by 2, right? Okay. So that looks like 10,000 meters per second squared. Right? All right, last step. The net force, which in this case is provided by the normal force, is mass times acceleration, which is 0.45 kilograms times 10,000 meters per second squared. So that was 4 places, right? 1, 2, 3, 4. Is that 4,500 newtons? Is that what that would be? All right, 4,500 Newton force. Okay. All right, guys, get there. Number 19. We got this bird feeder supported by 3 cables. Okay, well, there's one vertical cable, and then it branches and goes 2 ways. Okay? Find the tension in each cable. So the tension, this cable, this cable, this cable. Right? They told you the weight of the bird feeder, right? Which is kind of nice because it could have given you mass, but we actually do care more about weight, right? I mean, it's not accelerating, so we just care about the forces, not really the masses so much. Yeah, so you got 150 Newton. But what is the mass of the bird feeder? If it weighs 150 Newtons? Yeah, there you go, 15 kilograms. 15 kilograms. Okay. Let me dig up. All right, so yeah, actually got a couple posters for this, right? I got one that's symmetrical, looks like this, right? And then I've got an asymmetrical one, right? So a little bit more complicated. Let's start with that kind of simple one, right? Because they both involve the same principle. So suppose to look at this point where all the ropes come together, right? So got this down force and I got these these 2 tension forces. Right? Now, if it's all symmetrical, you could call them the same force, right? Same tension force or spring force in this case, right? But the principle to solve this is you can set up a system of equations where horizontally and vertically, all the forces have to cancel out. Right? In general, they cancel out, right? Because equilibrium. Right? You can introduce a Cartesian system and say, well, if you look at these side-to-side ones, this one pulls to the right as much as this one pulls to the left. So that's got to zero out. Right? And then each of these is pulling up-ish. And if you add those 2 upper components, that has to balance out with the weight acting down. Right? Right? Now, the more complicated version of it, which you guys actually have in the textbook we're about to solve, right, is what if it's asymmetrical like this? Right? So we got 2 different tensions like this, right? But the same starting principle holds, right? So this one will pull to the right as much as this one pulls to the left. So that sets up there. Right? Now we have a left force and a right force, so they're different values. So we got that. We have to juggle alpha and beta, and it looks like based on alpha beta, we got some cosine values going on, right? Right. So it zeroes out that way. Then vertically, these 2 upward components have to balance with this weight down, right? So again, there's a left tension and a right tension. We've got alpha and beta, but now we have some sine values, right? Sine of alpha and sine of beta, right? Subtract the weight down, that has to zero out too, right? Right, so if this was an FRQ, I bet that would be like the first point or the first couple points, just having the setup. Right? Even if you didn't solve it, you'd probably pick up partial credit there. Right? Let's go. All right. It's number 19 type. Okay. Gonna say, maybe something like this. Okay. So do a Cartesian system. Got a little under there. That. Okay. I'll call this the force on the left. I'll call this one the force on the right, okay, which are two different values. Okay. They gave you, oh, they gave you the angles, but they're like up there. Wow. Here. I'm just gonna make something up. Okay. Maybe I'll go, okay, let's call this 60 degrees. Let's call this like 30 degrees. Okay. And we'll call this one over here. Yeah, my picture's not exactly to scale, but I said, yeah, 60 degrees there, like 30 degrees here. Okay, something like that. Okay. All right. If I split this into components, split each of these top tensions into components, right? This guy's pulling to the left and up. We can quantify how much, sort of. And this guy's pulling to the right and up. Okay. Now, even though we don't know what those tensions are, what I can say is that whatever the tension is, so like the force on the left side we're solving for, okay, I can multiply this by cosine of 60 degrees, and it would represent that component. And this would be the force on the right times cosine of 30 degrees. Right? Just like that. Okay. How about vertical? Vertical, I got force left times sine of 60 degrees. And here's the force on the right side times sine and then 30 degrees. Okay, just like that. They also told us the weight. Here, I'll just use what the book. No. Yeah, I'll use what the book's got. Say 150 newtons. Okay, 150 newtons. Okay. One of your quiz questions is basically this question. Okay. Okay. So the tension in the bottom cable is just the weight, right? So boom, that one's easy. It's just 150 newtons. Okay. What about these other ones? Okay. Well, we have to set up a system of equations. So we're going to solve this with a system of equations. Okay. So let's go. The sum of the forces in the x direction goes to 0. Right. Oh, spell about to ring. It sure is. Okay. But you guys see the big picture setup, right? These two have to balance out horizontally, which is what I was about to say right there. And then vertically, these two up have to balance with this one down. You can do a system of equations, and then you can solve for everything. All right. So it's gonna be our pause point today. All right, yeah, you guys have a great Tuesday.